So, well, good morning, everybody, and thank you very much for electing to come and spend some time with us here today. My name is Reza Rokni, and I'm one of the solution architecture team here at Google. My role is to work on our fully managed data analytics platform. On stage, I'm very delighted to have Dan with us.
Good morning. I'm Dan Nelson. I'm head of data at Ocado. I've been at Ocado 15 years, so I hope I've got quite a good story to tell today.
Thank you, Dan. So what we're going to cover today is, first of all, we're going to walk through some of the fully managed services and how these actually make a deep impact for both the data engineers and data scientists in the organizations, how we can get them to do much more in the data science and machine learning projects that folks like Ocado are undertaking. And then Dan is actually going to cover how they've actually used those tools in a few projects, some of their future projects. And at the end, we're going to touch a little bit on the cultural differences that are kicking in as we have these new machine learning and data science projects. So we mentioned data scientists and data engineers. So what's the difference between those two? Well, if it was the beard, then the guy on the left would be the data engineer in that picture, and the other guy would be the data scientist, because I would actually consider myself to be a data engineer rather than a data scientist. But of course, as with all of these things, it is a spectrum. You will have data engineers doing more and more data science. You have data science who, by definition, because they're working with these larger data sets, have to do data engineering. And again, this is one of those dynamics that Dan will cover in terms of how that culture is being changed in these organizations. So what does a data engineer do? If we're imagining these guys are having a conversation, I can guarantee you the data scientist at some point in that conversation will use the phrase, and now we take the data and that single phrase is the bulk of the work that the data engineer will do. And in it belies a huge amount of potential complexity and work. So taking the data and then doing the data science involves collecting it, involves processing it. And as a data engineer, their role is to take the data, shape it, filter it, enrich it, and then land it into the systems that the data scientists can then be able to go and do the work that they need to do in terms of experimentation and ultimately to build models that can be used in production. So we mentioned auto-awesome. What is it about fully managed services that makes these things auto-awesome for data engineers like me? Quite often, people just associate auto-awesome with things like scale. So if I build a system and it's all API driven, I just write code, I've built my pipeline, I would expect that if I'm doing it for a POC and there's currently hundreds of messages a second going into this pipeline, tomorrow when there's thousands of messages a second or hundreds of thousands, I don't have to go and do a complete re-architecture. But it's not just about scale and resilience, it's also about a lot of the boring stuff. And this is the kind of stuff I, as a data engineer, don't want to do. Right? So I don't want to deal with things like logging and monitoring and maintenance. However, they are critical, obviously, for anything that you want to do in production. And this is why I think it's a really amazing time to be a data engineer or a data scientist at the moment, because we can really spend our time on the business problems rather than the tedious pieces. Myself, as part of the solution architecture team, I work very closely with our customers. So I've been working with Dan and Ocado for a few years now. I work with product management and our Google engineers back at base building these products. And our role is to take the things that we're externalizing and apply them to new, old use cases from our customers. And the reason I have such a fantastic time when I'm working with folks like Ocado is to prove out that a use case matches the technology only takes weeks in that proof of concept stage. Obviously, there's more work to be done while we then turn it into production. But that is the bit that makes it so much fun for us, because we don't have to spend time on things that I don't think add much value. Me writing some more code for doing logging isn't bringing much benefit to the customer. I've also got auto-testing in there. It doesn't quite do auto-testing, but what it does do is it helps facilitate the testing that we need to do. And the reason that this is all becoming important is because you want data science to be like software. You want your data science projects to be like software. The same way you deploy software today is how you want your data science projects to go forward. So what we're going to do is I'm just going to go through a typical architecture that we would put together using these fully managed services through APIs for two pieces of a project. The first piece is the data scientist has come to us and asked us, as a data engineer, can you please build me a pipeline that will get data that we're collecting within our company to the tools that I need to use? After that, I'm going to change that pipeline to make use of the data science project that the data scientist has created to put it back into a production system. So how would that architecture look like? So what are we trying to do initially? So we have data coming in to the system on my right, and that data could be anything. So it could be data from IoT devices from the robots in a factory. It could be clickstream information that's coming from the websites. It could be data from point-of-sale systems. All of this data, and for this architecture, we're going to use streaming. So imagine all this data is happening live, and we want to do real-time collection of that data. And we want to get it to what the data scientists want to use at the other end. So the data scientists, what are the tools that they can use? So Google Cloud Data Lab is a notebook style that data scientists will be very familiar with. Notebooks are great because they can actually do their experimentations with a notebook, keeping a note of what they've been doing at each phase. And I've seen data scientists use that as a way of presenting their results. So they'll go through at the end of the results, and people will ask, why did you use column A rather than column B? And they can go back to the beginning of the notebook and show the analysis they did that meant that column was a better use for the model that they're building. But also, Cloud Data Lab ties in very closely to things like BigQuery, which is our ad hoc analytics engine and data warehouse. And in there, if they had a query they wanted to run against hundreds of terabytes of data, they can do it without having to come to the data engineers to do a whole bunch of rework. Also, there is a session later on today around BigQuery where we'll show a demo of a single query being run over an entire petabyte of data. At the moment, that's still quite an unusual thing to do, but Dan will also talk about the amount of data Ocado is now collecting compared to the past. The other pieces they want to use is Cloud ML. So in building out their models, if they want to use TensorFlow, they can use TensorFlow to do distributed model building based on Cloud ML. But also, with Cloud ML, the prediction component comes with it as well. So once they've built that model, they'll be able to deploy that back into Cloud ML for the data engineer to then use in the infrastructure lifecycle. And I'll come back to that one a little bit later. And of course, then we also have our APIs. And then just some of them here, natural language API, the speech API, vision API. So as one of the data scientists at Ocado once told me, they don't want to write code that somebody else has written. So if there's already an API that's going to do some of the things that they want to do on the machine learning, why not just use those? Okay, so how do we get the data that's coming from your left to my right? Sorry, left and right still baffles me, obviously. First of all, we need to collect this data. So what I'm going to use is the Google Publish and Subscribe API. This allows me to go into a console, I create a topic. I don't stand any infrastructure up, I don't spin up and tell it how many messages per second we're expecting to get into this single topic. The topic can absorb hundreds of messages a second or hundreds of thousands of messages a second. Some of our customers are actually taking up to millions of messages a second. And as well as absorbing the data, it also acts as a massive shock absorber for the system. So imagine that you've got your pipeline that normally runs at tens of thousands of messages a second during the average day. We come up to Black Friday, and it's suddenly doing hundreds of thousands of messages a second. So it can actually absorb that and give the downstream systems time to scale out and get ready to process the hundreds of thousands of messages a second that are coming now. In order to process this, I'm going to use Google Cloud Dataflow. Again, I'm writing code, I submit the code, and what Dataflow will do is it will spin up the resources needed to do processing of the stream or batch data across the resources that are needed depending on the load coming in. Here, I'm mainly using it as a transportation mechanism. So I'm going to take the data and shape it and then put it into the next stages. We'll come to have a more sophisticated use case when we start going into production. So that data is now going to land in, and I'm sorry, I don't think you can see some of the boxes there, but it's going to land in our storage, so Google Cloud Bigtable for a fully managed NoSQL database, and BigQuery, as we mentioned before, where we can run SQL analysis against this data. At this point, we've now got a pipeline that is able to get data in real time to the data scientists to start running their analysis in. So for example, they want to run a piece of SQL, it's going to be up-to-the-date information, not stuff from last day or a few hours ago. They can access the BigQuery and Bigtable through their tools, but also they get access to things like data flow again. So if they want to do other types of processing, they can submit code and get pre-processing for the tensors that they want to build to run into Cloud ML. They also have access to things like Cloud Dataproc. So Cloud Dataproc is Google's managed Hadoop and Spark. So if they want to use the mlib libraries, they can go to Dataproc, spin up a cluster. It takes less than 90 seconds for about 10 nodes to be up and running, and then use that connected with the data that's in BigQuery to run some more analysis. OK, so this is a typical pipeline. Let's say we're doing the POC, and I've actually gone and built this. And this is the kind of thing that I will do. I've done with financial sector, in retail and manufacturing. Getting the basic pipeline usually doesn't take more than a few days up and running, and that's mainly around what the data should be moved around. Let's now say that we've had our successful machine learning project. The data scientist has done their amazing work and built something that's going to make a difference to the company. So now I need to turn this into a production system. So how much extra work do I have to do to that original pipeline? Well, if we built it using this fully managed system, actually not a lot. So as I said before, with Cloud ML, you can actually deploy the prediction component of the model that you built within the Cloud ML service as well. So now we're going to start doing a little bit more of a sophisticated data flow use case. Instead of just shaping the data and moving it downstream to our storage, we can actually run the inferences against the Cloud ML service, against that model that we built. And as we're doing this as the data is flowing, it's useful to then be able to react to things. So let's imagine there is a new way, the model is going to do some more interesting things around recommendations, and we want to push that back into the other systems so that we give the customer a better experience right now when they're on the website. So we can then use PubSub, again, this time not as an ingestion mechanism, but as a way for us to push the results into the Publish and Subscribe API, which can then go and connect to systems outside of the data analytics realms. So lots of companies will have the data group, and they'll have the infrastructure group who are dealing with the front ends. That would be the conduit for me to send this information as it's happening, after the inference has been done, to those other systems. So just a quick recap, just ran through a couple of scenarios where we can gather data and get it to the data scientists, how we can then productionize that. But always, actually, sorry, I have completely forgotten about one slide, and we'll just skip this one. So going over to Dan, who will show us how, talk through how Ocado has used some of these tools today.
Thanks, Reza. I'd like to do a quick survey, if I may. Could you put your hand up if you know who Ocado are? OK, that's pretty good. Better than normal. Could you put your hand up if you are a customer of Ocado? OK. Could you put your hand up if you knew that you were the customer of the world's largest dedicated online grocery retailer? OK, yeah, not a large known fact. Did you also know that, and put your hand up if you knew that Ocado isn't just the retailer, it runs its whole operation from the supply chain, the logistics, the warehouse. Okay? And put your hand up if you knew that Ocado writes all of the software to actually run that operation from the website through to the warehouse management system, through to our routing solutions. Yeah, no, we do. And we have over 1,000 engineers within Ocado, within a division called Ocado Technology, whose jobs are to make that software, to keep us innovative. We're in a really competitive market. We have a unique and a disruptive model, and our technology staff are there to basically support and drive our business in keeping ourselves competitive. And that has turned itself into us not just running our own operation, but as providing a platform to clients around the world so that they can run their own e-commerce solution, a world-beating solution, and run it at any scale. The at any scale is important because it changed the way that Ocado approached the software solution. We wanted to be able to scale these things out very quickly and to allow ourselves to be able to support our clients regardless of where they were and at what level they wanted to operate. And in fact, we guarantee as part of the contract a throughput of the warehouse, a throughput of the website, and these are very important things because in order to do that, we have to be super confident in the infrastructure and the tooling that we're using. Now, when we looked at Smart Platform, and you can see that it gives you everything software as a service to run your operation, to manage your website, plus all the fulfillment channels, including a warehouse and the proprietary technology we've built for fulfilling these orders. We chose Google Cloud Platform as the place we would take all of the data, all of the events that happen inside of this system, and store it and build smarts on top of it and expose it back to the retailer so they can build their own insights. And when we were doing that, we found the AutoAwesome that we've talked about was something that actually we could give ourselves back into the UK really quickly. When we built the Smart Platform, we had to build something to consume all of the events coming out of the Smart Platform, and that we did using Spark. Now, when Google presented us with a managed Spark cluster, Dataproc, we migrated ourselves into there so that we could remove all of the extra maintenance we were having to do on managing our clusters. When they then gave us Dataflow, we migrated all of that Spark logic into a Dataflow. And we were operating, we were trialing, we were using it with prospect customers, we were using it internally. Now, what was really important is when we took it from the UK, we deployed the same code, we put it into a new project to make it based for our UK operation, and we scaled it without any modifications to now hitting 250 million events a day. We didn't have to do anything. All of that happened underlying. Reza mentioned the amount of data that we now have in the cloud. We're now at 0.5 petabyte. This tooling has allowed us to basically scale up without any friction really to 0.5 petabyte. That is more than 20 times what we had currently been storing in our Oracle data warehouse. But where does all this data come from? So I mentioned our unique model. We have highly automated warehouses. We call them CFCs, Customer Fulfillment Centers, because they actually do the picking directly for a customer order. These warehouses are, or at least our kind of legacy traditional ones, are vast. They're about 4 football pitches as a footprint, 4 stories high, and they operate in multiple temperature regimes. They pick something in the region of 10 million items each a week. They pick around about 100,000 items an hour and make several million routing decisions a day. Our latest warehouses are robots operating on top of a Hive grid. You can find out more about that on the Ocado technology website, and operate much more like an IoT. They're emitting events in order to work out where they are in the grid all the time, and the volume of data is extraordinary. The thing is, though, that these warehouses live inside of an ecosystem. This ecosystem is very symbiotic. That means that all of the parts that we manage, from ordering through to delivery, need to operate in a very optimal way. A failure in one piece will lead us to basically degenerate other areas of the ecosystem. So in Ocado, we've spent, certainly as I say, I've been there 15 years, a large part of our time optimizing this flow. We want to make sure that we're predicting our demand really accurately so we can put really good orders in on our supplier, but do it in a way that means we get the product just in time to minimize our waste, but to give full availability to the customer. We want to make sure we're storing it in the right place. That's not just health and safety, the right temperature, but actually where in the warehouse do I put this to optimally make the picking flow as best as possible? And how do I put pickers into the right place? How do I move them around so I stop ourselves from getting blocked? Then making sure that the van is loaded in the right time and it's loaded carefully. And then ultimately, it's delivered in the 1 hour slot that the customer wants. Now, we've applied a lot of ops research, a lot of artificial intelligence in this space, but historically we did it in a model whereby we'd give a problem to a data scientist. The data scientist would go away with a big desktop. They would pull some data. They would spend several months working through different models. They'd end up with a model written in one of probably 5 different languages. It might be Java, it might be Scala, it might be Erlang. They would then try and give that to a development team and say, could you try that out for me? Could you productionize it? They would have to try and understand it. Then, if goodness sake, they wanted to go back and modify it, let me get that into your backlog again. And there was just so much friction, and it wasn't an optimal process. And that's a problem because all of these optimizations are about customer service. Everything about getting the ordering right and keeping the waste down is actually about giving the customer the product and allowing them to buy it. Getting the delivery on time, it's all about exceptional customer service. And Ocado has always put that at the front of everything that we do. Now, we're not perfect, and we do sometimes make mistakes. Certainly, things, because we use the roads a lot to make the deliveries, if there's a traffic problem, it can impact a large proportion of our customers. If we have bad weather, again, it might affect traffic, it might cause power cuts. And these sorts of incidents can be difficult for us to deal with. Or at least what we want to make sure is when we have problems, we're as capable of solving them as we possibly can. And that brings us on to the subject of today. Contact center is the main way that our customers get to speak to a human. You can see from the slide here that contact can be in many different ways. They might be asking for a refund. They might be giving us some feedback on a recent delivery or on the website. It might be a request for a new product. It might be to tell us they're not actually going to be in. Lots and lots of different things. Some of them happy things, some of them less happy things. And what we were doing is, as those emails were coming in from our customers, is we would put them into a queue. It would operate as a first in, first out. And we were getting maybe 2,000 of these emails a day. We set ourselves an SLA for first time to response, and basically man the contact center up in a way that we make sure we always hit that SLA. But what happened when we have one of these exceptional incidents? We might get 2-3 times as many emails. Obviously, the telephone lines get busy, so people start sending emails. They're actually of a more urgent nature, but they're also queuing up against those regular ones of, could I have a refund? Where do I find this on the website? So what happened one day around a water cooler in one of our development centers was the contact center engineering team were talking with one of our data science teams and said, can you think of a way that we might be able to solve this? So we thought, well, yeah, let's engage. A few months earlier, we'd started to bring data engineers into our data science teams in order to try and remove some of that friction I talked about before about deployable models. What we thought we'd do this time is another experiment. Let's put the data science and data engineers in particular into the contact center team, the software engineering team. Let's co-locate them, and let's get them thinking about what the best solution is. And let's start it really simple. This idea of how do I get more throughput in the contact center could end up as a chatbot. Maybe that's a way. Could be, let's just auto-close everything in a random selection. Could be, let's extend my SLA, and then I achieve it all the time. The important thing was, though, to get the data science guys into the software team and to get them into the business domain. So they actually spent time inside the contact center doing the job, learning where the process was challenging, learning where they might be able to bring value as quickly as they can. And from that, they basically came to the conclusion that there was a part of the process whereby, as an email came in, a human had to apply some context to it, a bit like this. This one, very typical. I love your website. I have children. It's easy to do the shopping. Many thanks for saving time. That would get, for instance, a tag of it is feedback, and it would also get a tag of customer is happy. So we're getting the context, and we're getting some sentiment. And what we wanted to do was to see, could we improve that? Because once I've got this information, I'm then able to make many more decisions over how I solve the problem. How quickly do I need to get to a resolution for the customer involved? So the team started simply. They looked to use code that people had already written. Working with Google, we had exposure to a very early incarnation of the natural language API. It was really great at giving us the sentiment, but obviously, as it's a service presented to us, it wasn't able to do the tagging. So whilst it was a great first attempt, and we learned quickly from what this might look like, we had to go and do something more bespoke. And that was where the machine learning piece came in. But machine learning was only the tip of the iceberg. So I'll go on to talk about how we built a TensorFlow model and how we've implemented it into production. But actually, the first thing was to get the engineers looking at what data do I have, how do I have to present it so that when we start looking at building this model, it's in a format that I can use, that it's reusable, so that when I have tried and tested and learned and reiterated, I can actually then push that forward and use it in production. As it was, we had a corpus of about 1 million emails that we'd stored on premise. It's about 3 years worth of data, and that looked like a great data set to use to train the model on. But we needed to get it to the cloud. We needed to honor our data privacy guidelines and controls. And so the engineers spent a very large amount of time basically redacting this data, removing outliers, and essentially building a pipeline that allowed us to push all of this information continuously up to Google Cloud Storage, whereby we could then train the model. It was a sizable amount of the time of the project. The project in total was about 6 months. I reckon, the learning, the initial kind of domain knowledge was a month. This was probably a good 3 to 4 months worth of the work overall. And then what was important is the team realized that it's actually only the code that matters. The business would love a solution as quickly as possible. They would love to start bringing value and to remove some of these problems. But what they don't want is to have something, and this is what Reza was talking about earlier, something that works for 100 emails a day, or even 2,000 emails a day. They want something that they know will reliably work and scale, that it'll be maintainable, that if they wanted to change in the early days some of the behaviors, it wasn't going to take months for us to do it. And so that was a challenge for the development team, for the data science guys, to basically come at this as a software engineering challenge, to make sure everything they built was reusable, to make sure that it had tests, to make sure where they made technical debt decisions, it was marked and that it would be allowed to be come back and fixed at a later date. So it was data science as software. As I say, this was not us approaching this as a science challenge. This was the business had gone to their development team in the contact center and said, how can you help us solve the problem? At that time, those guys did not have the awareness of the tools and the data engineering tool set that we had available. So we worked with them. to provide this solution, but it was always going to be their solution. So we wanted this to operate like a normal software engineering project. So we used Git. We put the code in, we built versions on it, we were able to deploy it using our normal pipelines. We used public APIs, so we didn't go rewriting things just because we were able to. It was, let's use the GS util. Let's use everything that is exposed, because then it actually helps the developers going forward. One thing, by the way, on Rez's slide, the AutoAwesome explanation, for me, is how easy this is to use and how accessible it is. I don't have these large lead times of, can I have a piece of infrastructure? I don't have to learn something specifically new. For these software engineers, it's an API call, right? It's nothing more complex than that. Clearly, I have to understand what the request and the response look like, but it's an API call. So that kind of barrier, the AutoAwesome is, it's really quick and easy to use. And then, of course, we've got reproducible and allowing those engineers who are going to end up looking after it to maintain it. So what did we build? Okay, if you look at it from my left hand, your right, first of all, we had to do the training. So as I said, we spent a large amount of time prepping the data, prepping those emails so that we could get them into cloud storage and run them through a training model using TensorFlow. We used Compute Engine at that time to do it. I'm going to caveat that this started probably about 12 months ago, so a lot of the stuff that Rez has been talking about, we have a rule that we wouldn't use beta in production, so we had to kind of come up with some of our own solutions. If we were to do this again now, that Compute Engine area would actually be CloudML, and we would use as much of the exposed managed services as we can. So we spent probably a month or so training our model, updating variables and parameters so we could get the best fit. But we also took a pragmatic approach of, let's not try and make it as perfect as possible. Let's get it working, deploy it, test it, and come back. So that's what we did. We deployed the tensor model, exactly the same one that we'd trained up on the Compute Engine, and deployed it into CloudML Engine. We exposed via the inference API the call into the model, and basically got the software engineering team for the contact center to plug in the email. Again, what we would have done nowadays is we would have used Dataflow to do that connection, but that wasn't something available to us on this model. It is part of the tech debt that we'd like to go back and fix. So now, when an email comes in, the contact center solution makes a call to the prediction model, and the model comes back with, here are the tags. It then goes through another iteration, not the model itself, which is what priority would I apply to this email based upon my knowledge of its content and its sentiment. We then make sure that we don't operate the FIFO model. We basically allow emails to queue hop based upon that relevant priority. Also importantly, though, we stream those decisions back into BigQuery and then allow the software engineering team and the data science team to measure the F-score and to measure the impact of these decisions that are being made. This is great. It's easy to integrate that. It's an API call. We then use data labs to represent that out to the business and have a consistent way of reporting back on it. So what was the impact? Well, as I say, first of all, one of the major impacts to me is we managed to turn this around with all of the learning that we had. We were using TensorFlow for the first time. We were using a lot of these tools for the first time. We had to learn about the domain. It took 6 months from idea to actual delivery and running in production. That's pretty amazing, I think. So that's one of my big impacts. But actually, there are some much more measurable things as well. So from a customer service point of view, We know now that we are dealing with urgent and, if you like, more negatively sentimented emails 4 times quicker than we deal with those which are positive and less high priority. And indeed, if we compare back to how quickly we respond to those negative ones, it's actually 3 times quicker than no filtering at all. So we can actually see that we've really deprioritized the lower priority one and increased the speed at which we deal with the higher impact for the customer. So that's brilliant from a customer service point of view. It's harder to put numbers on that because that impact on better service takes a long time to be visible in various other trends. But something that we can measure really easily, and that big number in the middle is absolutely true, not too many zeros, a 10,000% ROI. Why is that? Well, what we actually found as part of this was there were around about 7% of emails that we didn't need a human to actually interact with. What was happening is once they put the tags on, they would kind of go, oh, it's spam, close it. And actually, if you remove those, that action and redeploy those people in doing what humans are good at, the creative problem solving, we can actually redeploy 4 full-time employees and save ourselves £100,000 in recruiting them to scale out. Why 10,000%? Another part of AutoAwesome is the transparency of what these things are costing. I can tell you with extreme confidence that it costs about I know that sounds a bit weird, about £100 a month to run this service. It's about, because obviously our exchange rate is fluctuating at the minute, but it's about £100 a month to run this, £1,000 or so a year, £100,000 saving. The great thing on that transparency is it tells you that this isn't free. So I have to prove my ROI as a data engineer and a data scientist, but I have all the things I need to do that. In our previous incarnations, in those other models, do I attribute a small proportion of a DBA's time to it? What about a Unix admin? What about the hardware that I had to buy? What about the licensing? What about the storage? And how do I attribute those costs? I could come up with it, but it's much, much harder. Or do I just say, it already exists, it's free, and therefore my ROI is enormous? So the AutoAwesome isn't just for me about how quick and easy this is to use and how scalable, but actually how amazingly good it is at actually showing you where your business value is. And there were some other lessons as well. We learned, as part of this experiment of deploying people into the software engineering teams, that actually we might have to revisit some of the success criteria. Maybe that original SLA of first time to response isn't the right one. We might actually break that in the case of deprioritizing. So those ones with lower priority maybe now don't hit that first time to response SLA. So we have to work with the business to make sure we really understand what success looks like. And to make sure that we also don't just look at it in a fixed window, but we buy in with them that we will use data science, data analytics resource to continually measure and see how that performance of the model is working and the impact it's having on our customers. But beyond that, and beyond that efficiency that I said, the 10,000% ROI, better data and the reuse of these pipelines that we've done, the streaming of the information back into BigQuery, has actually helped us identify that we now can see when refunds are happening and happening at a scale which might indicate a problem. And if we can deal with that problem quicker, we can save ourselves money from an administration time, we can save ourselves money from a waste of product time, and we can actually improve customer service again. And again, cancel orders. If somebody's written to me to say, I'm not going to be in today, please don't make my delivery, we can now actually auto-respond to that and make sure that that cancellation gets processed without any human delay at all. Again, major cost savings to us. But what I also take away from it is the learnings that we've had in how we build these models, that cultural transformation. We no longer have to make these big sort of ivory tower long-term projects. We can get in and we can learn fast. We can look to bring the value as quickly as we can. We can fail it and we can try again. And that's really helped us as well on trying out new opportunities in other machine learning spaces, things like vision. We now understand how TensorFlow helps a data scientist access, and a data engineer, in fact, access models much quicker. We can give it out to software engineering teams, let them have a go, and not have to wait on our bottleneck of resource. So now we're looking at things like vision. We're looking at revisiting a whole load of those models that I was talking about in one of the early slides. How do we do better demand forecasting? What might anomaly detection look like as far as abnormal behavior of refunds and things? And what we've also got is the learning of what a standard tool set would look like. Google provides us with all of these tools like Dataflow and BigQuery, Dataproc, and that helps us push and democratize that type of learning out to our software engineering teams at large. Somebody in a meeting I was at recently said, we'd like AI to be the new Java. We'd like it to be accessible to all, easily understood, and the barriers of usage allow it to be deployed everywhere. And the other thing we learned is, actually, we need loads more data engineers. We've now started hiring data engineers directly into software engineering teams, like you might have a software engineer in test, like you might have a UX person there. We want data engineers in there, because actually a large part of the delay, that iceberg slide, is getting the data. If actually as part of the software engineering process, somebody is there building the pipelines, landing this data in the cloud, remember this 0.5 petabyte we've got and growing, then actually asking the questions is much, much easier because you've already got the data prepped and in a position where you can make use of it. If you'd like to learn more about what we've been doing, please visit the Ocado Technology website. It's just been relaunched today, so there's loads more to do with the blogs about how the actual engineers who did this approach the problem. And if you're interested in being one of our data engineers, then I'm sure there's some vacancies on there as well. Okay, thank you.
Dan. Thank you very much, Dan. I was just wondering, well, we've got a couple of more minutes. You talked a lot about the data engineers, the data scientists. Obviously, your team is expanding. It'd be interesting to hear a little bit about how your team's culture has been changing because of these tools and that interaction between, I know some of your data engineers are now becoming data scientists.
Yeah, I think what we're able to do is federate the problems down a lot more now. The things like speech API and vision API are a perfect example of abstracting away that kind of primitive and very specialist knowledge and exposing it in a way that people can basically make access to it themselves. So data engineers now are much more able to help in the actual solution and the driving of the idea. They may go to a data scientist if it falls into a specialist realm. They may fall in there just to have validation of their decisions. They can do certainly a good 80 and a bit more % without that. So culturally, it's just transformational in our ability to solve these problems. We don't now feel like we're going to have that bottleneck of where next can I get some data science time.
Great, thank you. And that's actually mirrors my own experience and a lot of experience as Googlers. I will start and work with customers like Ocado. I will actually be able to do some deployments of models based off my data engineering skills. We can take a stab at some of these things, and you can get reasonable results. But to take it to that next step, then I go back inside Google to our data science researchers, et cetera, to be able to up the percentages. And I think that's an interesting thing that's going to happen in these teams is there's going to be a ratio of data engineers and a few data scientists to help them along and be able to do lots more projects at these companies.
Yeah, I think we see it now that there's an aspiration now that people can traverse. I don't have to go away and do a PhD for 5 years to try and help in this. I may not achieve what that guy with the PhD can do, but I can certainly get part way there to accelerating this learning. So yeah, it's brilliant.
Great. Thank you very much for your time, Dan, and thank you very much for joining us in this session this morning.